In digital design, and more specifically in logic synthesis, the main goal is to identify a circuit that satisfies two key objectives. First, the circuit must meet the functional requirements specified. That is, it must perform the intended task correctly. Second, it should also exhibit good extra-functional characteristics, meaning it should be efficient and practical in real-world implementation. Typically, we want the circuit to be as small as possible. A smaller circuit requires less silicon area, which is critical when implementing the design on a chip. At the same time, we want the circuit to perform its function as fast as possible. In formal terms, this means minimizing the latency. That is the time between the moment input values are applied and when a valid output is produced. Now, there are also other important aspects that we will not consider in this course for the sake of brevity. An example is the power consumption. In fact, it's important to recognize that reducing power usage is essential to address the energy efficiency challenges typical of modern computing systems. To accurately evaluate the area and the performance of a system, we would need to fully implement the circuit all the way to the final chip. However, this is practically unfeasible because it is too complex, too expensive, and too time-consuming in terms of development time. Since we cannot build the chip just to evaluate the characteristics of a circuit, and since we also want to keep the logic synthesis process independent of the later design stages, we rely on methods to estimate the extra-functional characteristics. These estimates help guide the optimization process during synthesis, allowing us to identify the best possible solution. Now, this estimation must be performed at the highest possible level of abstraction. That way, we can quickly decide whether it's worth continuing the search for an optimal solution or if we should stop. In practice, during logic synthesis, we carry out these estimates based only on the structural properties of the logic circuit we are designing and not on its physical implementation. Furthermore, the estimation process must have a low computational cost. In other words, it needs to be fast. This is crucial because during logic optimization, we'll be exploring a large number of alternative implementations of the same specification. So, quick estimation is essential to keep the overall synthesis process efficient. For these motivations, logic synthesis uses figures of merit that are quick to compute and that provide estimates whose computation is independent of the implementation technology. Let's analyze the first extra-functional aspect, that is the area. The area, or more precisely the size of a circuit, can be estimated by summing the space occupied by its components and interconnections. In this context, the components we're referring to are logic gates. We assign each gate a cost, meaning a numerical value that reflects certain characteristics. For example, we may assign to the gate a value that depends on the type of gate. Moreover, such a cost may also depend on the number of its input lines. More inputs typically mean a larger physical size. Now, when it comes to interconnections, their area cannot be easily estimated at the logic level. That's because it depends on how the connections between components will actually be routed, which is something handled later during physical synthesis. For this reason, we typically assume that the area of the interconnections is proportional to the area of the gates they connect. Let's look at an example. Assume that each two-input and/or gate is assigned a unit cost, and NOT gates are considered to have a negligible cost, essentially zero. For the circuit shown here, which contains 3 instances of two-input and/or gates, the estimated cost would be 3. Let's now consider performance. As we mentioned earlier, latency is the time between the presentation of input values and the generation of a valid output. So, latency can be estimated as the propagation delay of signals along the critical path of the circuit, that is the longest path that connects inputs to the output. The propagation delay through a logic gate is known if the technology library is specified, and it also depends on the number of inputs and the fan-out of the gate, that is, the number of downstream gates connected to its output. It's important to note that since different gates can potentially have different delays, the critical path must be defined as the longest in terms of time, not simply the number of gates, between the inputs and the outputs of the circuit. Finally, we cannot evaluate in a relevant way the signal propagation delays in the interconnections at the logic description level of the circuit. Therefore, such delays are typically neglected in this phase. Let's look at an example. Assume that each 2-input and/or gate is assigned a propagation delay of tau and NOT gates have a delay of 0. For the circuit shown here, the estimated latency would be 2 tau, since the longest path from the inputs to the output passes through 2 gates, each with a delay of tau. Let's wrap up this introduction on figures of merit with a few final considerations. For each extra functional characteristics, different figures of merit can be defined. These may vary in terms of computational complexity and estimation accuracy. Generally speaking, the more accurate the estimate, the more complex the calculation required. However, keep in mind that increasing algorithmic complexity to achieve a better estimate might not actually bring any real benefit. This can happen for several reasons. For example, in the subsequent stages after logic synthesis, such as technology mapping, the structure of the circuit may be significantly altered. As a result, an accurate estimate made earlier in the process might no longer be valid once those changes are applied. The goal of two-level logic synthesis is to minimize the size of the circuit, in terms of the number of logic gates required to implement the circuit. So, we are primarily estimating the area of the system. In two-level logic synthesis, we do not use to consider latency, because assuming a delay model where each n input gate has the same delay, a two-level circuit will always have a fixed overall latency of 2. Nonetheless, if we adopt a more fine-grained delay model that also accounts for the number of inputs to each gate, it can be shown that, since the reference model maintains 2 logic levels, minimizing the circuit size also positively impacts its latency. There are 2 commonly used figures of merit for estimating the size of a circuit expressed as a sum of products expression: the cardinality, which is the number of product terms in the expression, and the number of literals. In the upcoming slides, we'll examine each of these in detail to understand what aspect of the circuit they measure. Finally, do note that we here focus on SOP expressions. However, we can apply a dual reasoning to product of sums forms. The cardinality estimates how many and/or gates with any number of inputs are needed to build a circuit. When we consider a logic expression in SOP form, cardinality is defined as the number of product terms. This directly corresponds to the number of AND gates in the circuit. The number of OR gates is constant and equal to 1. If we want to refine our model, we can observe that product terms made up of only one literal do not require an AND gate. Therefore, these can be subtracted from the count of AND gates. In summary, the total number of AND OR gates, regardless of input size, is equal to the cardinality, that is the number of product terms, minus the number of single literal product terms, plus 1. Let's look at an example. Here we show a logic expression along with the corresponding circuit diagram. By analyzing the diagram, we count a total of 4 gates. Now let's compute the cardinality. Based on the data in the table, we identify 3 product terms. If we add 1, which accounts for the single OR gate, we get a total of 4, which matches the number of gates we counted in the circuit. Now, let's take this second circuit, where we count 4 gates in the diagram. We compute the cardinality, as shown in the table, obtaining a value of 4 product terms. Now, we subtract 1, which accounts for the product term that contains only 1 literal, since it doesn't require an AND gate. Then we add 1 for the single OR gate in the circuit. The result is 4, which matches the number of and/or gates we observe in the schematic. Let's now move on to the number of literals. The count of literals in a SOP expression estimates how many 2-input equivalent and/or gates are needed to implement the corresponding circuit. The number of 2-input equivalent and/or gates corresponds to the number of literals in the expression minus 1. Let me show you how this formula is derived. In a SOP form, each product term with n literals contributes to the final circuit with n minus 1, 2 input equivalent AND gates on the AND plane, and 1 new input to the OR plane. Let's look at an example. The term ABC can be implemented with two input equivalent AND gates, since 3 literals minus 1 equals 2, and 1 new input to the OR plane. This is shown by the green arrow in the diagram. Now, if we have a logic expression with L literals spread across K product terms, then the number of 2 input AND gates is L minus K. The number of 2 input OR gates is K minus 1, because combining K inputs requires K minus 1 2 input OR gates, as shown in this example. If we sum these two contributions, the K values cancel out, and therefore the total cost becomes L minus 1. Here's an example. The slide shows a logic expression and the corresponding circuit. It also illustrates, for each generic N input gate, the number of equivalent 2 input gates required to implement it. We count the 2 input gates and obtain a total of 7. Now, let's count the literals in the expression. We find 8. So, 8 minus 1 equals 7. As you can see, the calculation checks out.